Hello, today we're going to talk about geometric sequences. So another special type of sequence. You've already learned about arithmetic sequences, which were basically just linear. And so geometric sequences, they're sequences in which successive terms have a common or constant ratio that we'll use the variable r to represent. So a similar definition, but this time it's a ratio instead of a difference. So when I think about ratio, I'm thinking about division. Every time I divide successive terms, I should get the same thing, a constant. You've already seen some of these happen as well, and geometric sequence are also just exponential functions. And in these exponential functions, we've already written some like that, the r is the ratio, or it's the value that you repeatedly multiply by to get the next term. R is the base in the exponential function. Okay, so here's just a quick example, 2, 4, 8, 16. And so we've seen something like this where you're multiplying the previous term by 2. But thinking of why it's geometric, we would say a term divided by the one before it is the same every time. 16 over 8. And so we get 2 every time, so that means the common ratio is 2. And so I'll get into kind of a more formal way of writing these geometric sequences, their explicit rules, in a minute. But what I want to ask you to do now, similar to yesterday, or the last video, is to prove that this sequence is geometric. The sequence defined by 1/2 times 2 to the n is geometric. And so to do that, we need to make sure that there's a common ratio every time I divide successive terms. I don't want to go through just a list of terms and divide them. That's not enough to prove that it works for the entire sequence. So I need to instead think about it this way. I need to take the current term divided by the one before it, and every time I do that, I should get a constant, and that constant is r. What does that look like when I actually use the formula? Well, the current term is basically a sub n. The previous term is a sub n minus 1. So a sub n is just the defined sequence, 1/2 times 2 to the n. A sub n minus 1 is basically what I get when I substitute n minus 1 into the explicit rule. And so I'm going to divide these and see what happens. We can already see that the 1/2s are going to cancel. And so now we're down to 2 to the n over 2 to the n minus 1. And we know that when we divide terms with a common base, we can subtract their exponents. So I'm looking at 2 to the power of n from the numerator's exponent minus the power of n minus 1 from the denominator's exponent. That becomes 2 to the n minus n plus 1, or 2 to the first, a constant. And because we got a constant, we know that yes, in fact, this is a geometric sequence with r equal to 2. Okay, so what we'll do now is come up with this standard form for writing geometric sequences. And that standard form comes from something to this effect. For a sequence to be geometric, we know we start with the first term, a1, and the next term we would multiply by something. We'll use r. The next term, we multiply by r again. We're up to r squared. To get the next term, we multiply the previous term by r again, and you can see what's happening in this sequence. So if I want to represent that this is happening for n terms, I can say the first term gets multiplied by r how many times? Well, when I'm on the first term, it's not multiplied by r at all. So this one has an r to the 0. When I'm on the second term, it's r to the first. Third term, r to the second. Fourth term, r to the third. You can see that our exponent is decreased by 1 to get that explicit rule. This is the explicit rule for writing a geometric sequence. And we like this form because we can see the first term and we can see the r in the actual equation. How would I do this recursively? Once again, you would define your first term, and when we write recursive formulas, we want to make sure we do some kind of math to the previous term. A subscript n minus 1 represents previous term. What am I doing to the previous term? I'm multiplying it by r. And so this is your recursive rule for a geometric sequence. Make sure you can see that on the video.